Welcome to another fibre laser learning lab. Last time we built a foundation on the colour gold. Today we're going to try and consolidate that foundation a little bit more because we can't really build up on the walls of the house until we've got a good foundation. And there are a couple of big questions that I would like to answer before I go forward. I've heard that there are three major problems with putting colour onto stainless steel. There's a fairly narrow range of parameters for each colour. Well, I think last time we discovered that there was a fairly wide range of opportunity for gold. Now, I only tried 4 nanosecond pulses, but within that 4 nanosecond pulse there was a huge range of possibilities that existed for finding gold. But I want to look at the other possible problems today as well. One of them is the thickness, or the, if you like, the thermal conductivity of the material, which will pull heat away from the actual work surface, and it will change the colour, so I'm warned. And unrelated to that thermal conductivity is air temperature. In other words, if it's a hot environment, you will get different colour results to if it's a cool environment. So we're going to test the stability of the golds that I found. Was it fool's gold, or is it the real thing that will resist changes of temperature and changes of thermal conductivity in the material? As we saw last time, there are many types of gold. Those that are gold but don't show up only in a certain light. And there are those sorts of gold, here and here, which are pretty good at being viewed in all sorts of lighting conditions. Now these are the golds that I want to look at today. I've searched through the colour swatch that I produced last time and identified, and I've highlighted them here, those colours that were sparkly. 6 or 7 of them, which are what I call good quality gold. What I want to find out is, are there any common factors that give us some clues as to what produces what type of gold? I think the answer is yes. There's a bit of an odd one there at 1250 millimeters a second, but most of the sparkly ones, if you notice, are up here in the 1600 to 2000 millimeters a second range. And then we start taking a look at the gold. We had a light gold, and then we had the slightly coppery coloured, what I would call rose gold. So we've got 4, 3 and 2.5, which produces light gold. And if you remember, when we looked at the pulse per square millimetre density, we've got numbers here which are 100k. Now when we went to rose gold, the parameters have tightened up quite a bit. Although we had 1597 there, that's basically the same as 1600, and they're both the same, so you would expect those two to be the same. But then we've got this one here at 2000 with a slightly smaller pitch, 1.6 microns, and that gave rose gold as well. And again, when we looked at the pulses per square millimetre, these are in the 156k. So there appears to be a colour difference that we can identify from pixels per square millimetre. And tie that in with the microns that we're using, it gets us a nice rose gold colour. So we're going to start off today by just reproducing this result here, which should be a nice rose gold. Okay, so we've got a nice solid gold there. Okay, so the first test I'm going to carry out is using my thermocouple here, my K-type thermocouple, which is sitting directly under the heated area. Now, this will just basically check the thermal conductivity of the heat zone through this very thin 0.5 or 0.7 thick stainless steel. So, probably my hand heat has pushed the temperature up a little bit. The air temperature in here is round about probably 10 degrees C. So I'm a few degrees higher than the ambient. But let's not get too concerned about that. And hey, you saw what the temperature went up to, 70 degrees C. Okay, so let's turn this little cold workshop into summer, should we? We'll turn this piece of metal into something about 40 degrees C. That's a pretty warm summer's day. There we go, one warm summer's day. Oh dear, 65. Colour change? What do you think? So there's myth number 2 blown out the water. It's not very temperature sensitive at all. Let's go at myth number 3, which is thickness of material. Now I haven't got any really thick stainless steel, but for the purpose of this very, very small test, we've gone from 0.5 to something like about 1.6. So we're more than 3 times the thickness. And what I'm going to do, I'm going to do the test right in the middle of the piece of material. So I've got the maximum amount of heat being sucked away. This is basically the heat being pulled away from the surface by a much larger thermal mass. So let's see whether this has an effect on the colour that I'm producing. It's also a mechanically polished stainless steel this time, as opposed to a piece of bright annealed, maybe slightly redder than these first 2. So it is possible that there is some small degree of variation with temperature or with heat sinking. So we're not going to dismiss it completely, but what I would say is it looks as though it's fairly resilient to the 2 extremes that I've just tested. So it takes my fear away from the possibility that I may have discovered fool's gold. Now I think it's pretty real, and that we can work with general workshop parameters and not worry too much about the colour. And we have just shown that at 2 microns it's a pretty durable colour, resisting both heat sinking and temperature rise. But what these results seem to indicate, sparkle over here and colour over here, because here we've got the first 4 results between 4, 3 and 2.5 giving us a light gold, and then we've got these second 3 results here which are giving us a rose gold to a 1.6 micron pitch. So the indication here is that if we go from say 2, which is what we've seen our nice rose gold as, to 0.05, in other words half a micron pitch, that's a fairly significant change in the heating effect that we're going to see into the material. Are we going to push this rose gold towards a purple or a mauve? Let's give it a try. That's a pretty nice powder blue, sparkly powder blue. So my first shot will be to calculate quickly how many pulses per square millimetre it took to achieve that. And then we'll try a few more variables to see whether we can repeat that colour with different parameters. I've just calculated pulse density for powder blue and it's 625,000. So I've done a quick calculation, and to check the extremes of what we found before for sparkliness, roughly 2000 and 1200, the pitch becomes 0.4 microns and 0.66 microns. We'll try those 2 numbers and see whether we can replicate powder blue. Now that is weird because that's 1600 millimeters a second, half a micron, 2000 millimeters a second, 0.4 of a micron, 1200 millimeters a second, 0.66 of a micron, 1000 millimeters a second, 0.8 of a micron, 900 millimeters a second, 0.9 of a micron, and 800 millimeters a second at 1 micron. The rule seems to hold up except that one. There's nothing wrong with my calculations. These are all done with exactly the same calculation in a spreadsheet. I really don't understand why that should be different. The principle involved here is very simple. We've got exactly the same number of pulses per square millimetre, which technically means we should have exactly the same heating effect per square millimetre. The only difference is we've changed the relationship between the pulses across and the lines down. Now, in general, it looks as though it doesn't make any difference, but in this particular instance, for some strange reason, it does. That's a bluey green, that's a nice powdery blue, I suppose, and these are, I suppose, edging towards a green rather than a blue. I can see clearly that that one has got a smoother effect to it. As we decrease the speed, we're putting more pulses in the horizontal direction, and we're producing a smoother effect. It would appear that the roughness or the texture on the surface comes from running at the higher speeds as I anticipated before. I mean, to get blue, we've actually got to drive right through this colour range here to get towards the hotter part of the spectrum. And obviously by closing up the pitch, we're putting more heat into the material. I mean, logically it does make sense that I should move from here to blue, although I didn't think that it was going to be as extreme as that. I thought it would move from that to red first as we start moving in towards the hotter zone. We won't know until we really go and have a look at these under the microscope. Okay, so here's our puzzling image. It's a sort of a purpley gold. So what happens when we change to, say, 0.55? We've got half a micron and there's no apparent difference. So let's go down half a micron. It looks like the same picture because that's what the colour is on the surface. It's exactly the same colour when you look at it in normal light. Okay, so let's go back to this image, which is the starting image. And this time, instead of changing the pitch, we're going to reduce the speed to 1900, which means we're going to reduce the number of pulses in this horizontal direction. We're getting a little less mauve and a little more blue. So now we reduce it to 1800. Now we're getting a lot more blue and a lot less pink, although the yellow hasn't changed very much. So now we reduce it to 1600. A little less pink. We've got some green coming in a bit now, but it's still rough, as you can see from the texture. Now we're at 1600 and we've virtually lost all the yellow and we're just into shades of blue and green now. And sure enough, the colour is coming out as a very nice blue. Now we're at 1500, still a nice sparkly texture. More green, less blue, no yellow. Now we're going down to 1400. Now look what's happening now, 1400. Can you see all these sort of blotches coming in and these blobs? We're getting much more of a flatter surface now. This is what this is indicating. Although we've still got some sparkliness in there, we've got areas where the surface is basically flat. And now we come down to the final test, which is 1300. We've still got a moderately rough surface there. It is sparkly. Now, what you must remember is there is no green in these tempering colours. So these colours that we're seeing here, they must be a combination of light rays which are creating colours that are not really there. And these are the colours that we can see at high magnification. Once they get drawn away and get to your eye, these colours don't exist. What you see is an amalgam of these colours. I haven't done the calculations at the moment to see what degree of variation we've got in the pulses per square millimetre count across this range of colours. I will go and do that shortly. We've just come across coppery gold again. Okay, so let's run again with 2 microns. Well, I have to say it's a bit difficult to say what that colour is. It's almost just a blank brown. It's certainly not sparkly. So I think we'll try and put some sparkle into that by increasing the speed, which is the formula for sparkliness so far. We'll push the speed up to 1600. Okay, now by pushing the speed up, we've decreased the heat. And we've got our copper colour back again, which is virtually the same as these two here. Let's see if we can lighten the gold by putting the speed up, leaving the pitch at 2 microns. Well, yeah, we've gone lighter and we've also gone sparklier. And those two there were done with a 4 nanosecond pulse, but this time we've got our nice coppery gold, rose gold, at 6 nanoseconds as opposed to 4 nanoseconds. So I wonder what happens if we go 2000 and something like 0.5 of a micron. Well, the answer is it gets us back to this strange brown colour that we had here. It's not sparkly, it's a dull brown. So I'm not interested in that really. I mean, it's obviously part of the colour spectrum. It's going to take a long time to produce it at 0.5 of a micron. So I'm trying to see if I can get nice colour and relatively high speed. Let's jump up to another power band. Let's try 8 nanoseconds, which will be at 250 kilohertz. And we'll start off again, what should we say, 1200? Let's say 8 microns. Well, we've got a sparkly coffee colour there that's nearly gold but not quite. It's like a white coffee. And we'll do two things. We'll first of all put the speed up to 2000 and see what happens. So we're decreasing the power, which means we might move towards a sparkly gold again. Yep, that's actually not bad. That's even more. That's a bit of a copy of this one, or some of these here and these down here. So we found rose gold again at another set of parameters. Yeah, we'll take the vertical lines down to 6 micron spacing. So we're adding some heat now, which might drive us towards blue. Yeah, there's definitely a blue tinge in there. It's no longer copper. So let's push it one more down to 4 microns, which increases the power per square millimetre. And that's done something really weird. We've got a sort of a green on the ends and a gold in the middle. Now that must be created by some really weird heating effects, because we are scanning like this. So that means we're getting double the heating effect at each end, like that. Hot there, turn round, hot there. So this is very hot, this area, and then as we scan across this middle area here, we've got a cooler zone, and that's exactly what that pattern there seems to be showing. I'm sure you can see that in this light. Let's just zoom in on that. There we go, look, you can see that clearly there now. Gold in the middle and green at the ends. So does that mean if I go down to 2 microns, I might be finding a sort of a peppermint green? Well, the answer to that question is no. We've gone to a very nice coffee colour, a very nice sort of a... But you'll notice something else in here as well. Look, we've got the same effect that we had here. We've got the ends, which are a different colour, to the centre. Well, all of this is very interesting, and we're getting further and further away from gold, but we are effectively trying to see if there are any patterns in the data that we're getting. I'm still trying to see whether or not there are any rules for colours. And this one here, again, it's a colour that's at 2 microns. That's a nice coincidence that we've come across many times before. And at 2000 millimetres a second with a different pulse. Now we came across this lovely but very positive mid-brown. And if we take a look here, look at the texture of the surface. We've got all these little blobs on the surface here, little raised portions. So let me just bring one of them into clear focus, and that's 41 microns. Let's just see how that relates to the background out there. And that's 39, 38. So that's about a 3 micron difference in depth, which is substantially more than the thickness of the film itself. So we must be disrupting the surface of the metal to make that amount of distortion. So I did the calculations for that mid-brown and found it was 62,500 pulses per square millimetre. Now I changed from 2000 at 2 microns to 1000 at 4 microns. Okay, now that looks like a modern artwork. But even though that is different, it still comes out looking the same matte mid-brown. That is a huge change in terms of the speed, going from 2000 to 1000, and the line width from 2 microns to 4 microns. We get no apparent change of colour, even though you can see that it is significantly different down at this level. So here we are at 3 microns and 1333 millimeters a second. Again, look, we've got these little raised blobs here, but they're not as pronounced as they were in the first one, but we've still got lots of yellow in the background. And we've still got the same apparent mid-brown, despite this slightly different surface texture. So we upped the speed again to 1600 millimeters a second and dropped the pitching to 2.5 microns. We've got our blobs here with mauves and browns, and we've got yellow in the background and gold and red. The net result of this is still a mid-brown. So we've got a very wide range of opportunity to get this lovely mid-brown blank colour. I think I'm going to have to produce a separate swatch with a record of each one of these colours on it, so that we can see what our progress is and what the lovely range of colours that I shall be able to put onto this palette. So although I've been supplied with a recipe of colours from Lotus Laser, I have to say I've not opened the files at all. I'm going my own way at finding colours with my method, because I'm looking for a different sort of colour that normally you see on these palettes. Now, I'm feeling fairly happy with that swatch, because even in this white LED light, we've got some nice colours. This is not daylight. This is a thing that was defeating other systems. That should be green. Those should be, I think that's pink. And that one's gold. That one's gold. I think these are supposed to be a purple. And I think these are silver. This one is supposed to be like a sky blue, and it's come out as a sort of a bit of a grey here. The colour recipe that I've been given is nothing like the recipe that I'm looking at here. Now, we accidentally came across this setting. Doesn't look particularly different to some of the golds that we've seen. You know, it's got light pieces in it, yellow pieces, a little bit of pink in it, some blue. What colour do you think that's going to come out to? Now look at that. Isn't that beautiful? Because look, I can get the top of that lump into focus now. Let's call that 90. Well, look, the bottom is just here somewhere. I'll just bring that little bit of brown into focus there. And that's only 88, so that's only 2 microns difference. What colour would you think that is going to come out at? Okay, you've had enough time. The answer is matte black. Don't ask me why. Just mention it in your prayers tonight. See if you get an answer. So, thanks again for your time and patience, and I'll catch up with you in the next session.